Trevor Galley, and for my global water issue, I'll be going over nutrient loading from nitrogen deposition. I will start this presentation by going over the ecological issue of eutrophication, and then I'll be going into the sources of eutrophication or excess nutrient loading to water bodies, the type of nitrogen in the atmosphere, then the sources of reactive nitrogen in the atmosphere that contribute to nitrogen deposition, then examples of nitrogen deposition contributing to water quality issues throughout the world, and then finally some control and abatement practices that can be used to control nitrogen emissions to the atmosphere. Of nutrients in bodies of water. The nutrients are particular nitrates and phosphates. The nutrients induce changes in phytoplankton, contribute to algal blooms, and stimulates other plant growth within water bodies. As you can see in the picture on the top right, that is green algae in the Chesapeake Bay. And when plants and algae die, they sink to the bottom of the waters and start to decay. This decaying process depletes the bottom strata of the waters of oxygen concentrations, which is also called hypoxia, and the waters become uninhabitable for aquatic life. In some waters, the range of hypoxia are the complete depth of the water bodies, and in these ranges, they're usually called dead zones. And I think the most common dead zone known to the general public is the hypoxic zone within the Gulf of Mexico, just near the Mississippi River Delta in Louisiana. As you can see in the map on the bottom right, any location, red or dark red, within the black line has a dissolved oxygen concentration below 2 milligrams per liter and cannot support aquatic life. Agricultural sources from chemical fertilizer and manure runoff, urban and industrial discharges containing high nitrate and phosphate loadings, and then finally nitrogen deposition from the atmosphere. And the EPA estimates that up to 44% of nitrogen loading to coastal water bodies comes from nitrogen deposition. There are two main categories of nitrogen in the atmosphere. There's unreactive nitrogen, which is just N2 gas in the atmosphere. Our atmosphere is 79% N2 gas, and N2 gas is very unreactive because of the triple bond between the two nitrogen atoms. And then there's reactive nitrogen with oxides of nitrogen, or NOx, and there's 7 compounds collectively known as NOx, and they are NO, or nitric oxide, NO2, nitrogen dioxide, N2O, nitrous oxide, N2O2, dinitrogen dioxide, N2O3, dinitrogen trioxide, N2O4, dinitrogen tetraoxide, and N2O5, dinitrogen pentoxide. NO and NO2 are the most common. NO is usually formed by a combustion reaction and then is rapidly oxidized to NO2 in the atmosphere. The EPA only regulates NO2 as a surrogate for NOx because it is the most common form of NOx in the atmosphere that is generated by human activities. And then there's also reduced nitrogen in the atmosphere, which is mainly gaseous ammonia and aerosol ammonium. Sources of reactive nitrogen in our atmosphere. NO comes from bacterial action in soil and lightning strikes and forest fires, so NO from naturally occurring combustion. This biogenic NO emission sources account for less than 10% of the total NO emissions in our atmosphere. And then there's also nitrous oxide emissions from bacterial action in soil from the denitrification process you can see below. And then there's anthropogenic or human-generated sources of reactive nitrogen, and these come from NOx, from combustion emissions, from road and non-road engines, coal and natural gas-fired power plants, and heating sources. NOx also comes from power plant flue gases in the form of N2O3 and N2O4, and nitric acid production facilities in the form of N2O5. And then Raising livestock is associated with ammonia emissions, and ammonia is the pollutant responsible for most of the nitrogen deposition in rural areas. Chesapeake Bay, where over 33% of the nitrogen pollution is contributed to nitrogen deposition from the atmosphere. The Chesapeake Bay has an airshed approximately 570 square miles, which is nine times the size of its watershed and extends from Indiana all the way through the Atlantic Ocean. The NOx emissions or NOx pollution to the Chesapeake Bay has been decreasing, however. In 2000, NOx accounted for 75% of the airborne nitrogen pollution. And then in 2017, it accounted only for 50% of the airborne nitrogen pollution. And the total nitrogen loading to the Chesapeake Bay has also been decreasing, mainly because of regulation from the Clean Air Act. In the Baltic Sea, 25% of the nitrogen pollution is contributed to nitrogen deposition from the atmosphere. Ammonia is the largest contributor of nitrogen to the Baltic Sea. And then, of all the countries surrounding the Baltic Sea, Russia and Germany contribute the majority of the air emissions to the Baltic Sea, with Russia contributing 40% and Germany contributing 30%. An emerging concern is NOx emissions from international shipping. According to estimates in 2004, NOx emissions from international shipping traffic on the European seas increased more than 28% from 1990 to 2000. And NOx emissions from international shipping are estimated to surpass NOx emissions from all land-based European sources by 2020. Contributing to water quality issues is a study by Spokes of the North Sea. She studied export of airborne nitrogen deposition from river watersheds in Europe into the North Sea. So two of the rivers she studied were the Rhine River in Germany and the River Thames in England. And she found that 16.2% of the nitrogen was attributed to nitrogen deposition to the river watersheds themselves before they flowed out into the North Sea. And finally, I'll talk about control and abatement of nitrogen emissions to the atmosphere. Hardwood forests act as nitrogen sinks, so as we can maintain and even increase the amount of forested lands on Earth, they'll decrease the amount of biogenic available nitrogen to the atmosphere. Improved agricultural practices can help control ammonia emissions. And then there's three main ways to control NOx. There's combustion temperature control methods, chemical reduction of NOx, and then sorbent injection to strip a gas stream of the NOx components in it. I'll be going over two forms of combustion control methods: use of low NOx burners and flue gas recirculation. Low NOx burners reduce NOx emissions in two main ways. There's a fuel reburning zone where fuel is added to chemically reduce NOx emissions. And then there's a final combustion zone where excess air is used to keep temperatures low enough to limit NOx production. Recirculation of flue gases reduces NOx in two ways. The flue gas in the combustion reaction dilutes the oxygen content of the gas stream being combusted, and the mass of the cooled flue gas stream also causes the heat of the gas stream being combusted to decrease below optimum NOx formation temperatures. There's two ways to chemically reduce NOx. There's SCR, which is selective catalytic reduction, and SNCR, selective non-catalytic reduction. SCR is one of the most effective NOx reducing technologies and utilizes a catalyst to chemically re-inject ammonia into the gas stream and to reduce NOx emissions. During SNCR, ammonia or urea is injected into a boiler duct or a combustion chamber where the temperatures are between 900 and 1100 degrees C to chemically reduce the NOx. The temperature range is critical for SNCR because the technology is based upon temperature ionization instead of use of a catalyst to change the reaction kinetics. For sorbent injection, sorbents such as ammonia, powder limestone, aluminum oxide, or carbon are used in either adsorption or absorption of NOx and other pollutants like sulfur. For listening to my presentation on nitrogen deposition from the atmosphere, and if you have any questions, you can reach out to me. Thanks.